Hello students, today we are going to discuss theories of bonding in metals. Theories of bonding in metals. Currently, scientists know of 118 different elements. About 91 of the 118 elements in the periodic table are metals. It means that most of the elements which are found in periodic table are metals. There are 17 nonmetals in the modern periodic table. Most of them are gases: hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. One is a liquid, that is bromine, and a few are carbon, phosphorus, sulfur, selenium, and iodine. The metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine are the elements found step-like line between metals and nonmetals. Characteristics of metals. Metals possess a peculiar shine on their surface called the metallic luster. Metals have high density and are hard substances. Metals have high melting point and boiling point. Metals are good conductors of heat. Metals have high electric conductivity, which decreases with temperature. Metals have high elastic nature. Characteristics of metals. Metals are malleable and ductile, that is, they can be hammered into sheets and can be drawn into thin wires. The property of converting metal into wires is called ductility. The property of converting metal into sheets is called malleability. So, metals are malleable and ductile. Metals are opaque to light. Metals form solid solutions called alloys with each other easily. Metals form solid solutions called alloys with each other easily. Metals are generally electropositive elements. Metals are generally electropositive elements. Finer the metallic particles, more reactive is the metal. Theory of bonding in metals. Metals are believed to possess a special type of bond known as metallic bond. The nature of metallic bond is explained in terms of theories, namely free electron theory, valence bond theory, molecular orbital or band theory. So, the nature of metallic bond can be explained on the basis of three theories. Let us discuss them in detail. First one is free electron theory. Free electron theory was proposed by Drude and Lorentz to explain the high electrical and thermal conductivity of metals. Some of the atoms lose one or more electrons but are free to move throughout the metal. Thus, these free moving electrons are said to be delocalized. Thus, according to this theory, a metal may be regarded as an assembly of positive ions. Metal may be regarded as an assembly of positive ions around which electrons are embedded. Cations immersed in a sea of mobile electrons. See, according to this free electron theory, a metal may be regarded as an assembly of positive ions, that is cations, immersed in a sea of mobile electrons. Weak bond. Metallic bond is a weak bond. Valence electrons are attracted simultaneously by a large number of atoms. Net bonding energy is very small and the bond formed is weak bond. Free electron theory. Thermal conductivity. When a part of a metal is heated, the electrons in that part absorb energy from the source of heat. These energetic electrons move to the cooler part and transfer the kinetic energy to the electrons present in that part on collision with them. And the process goes on till the temperature of all parts of the metal becomes same. Electrical conductivity of metals. Metals are good conductors of electricity due to the presence of mobile electrons in metals. When potential difference is applied across a metal sheet, free electrons start moving towards anode. New electrons are discharged from the negative electrode, leading to continuous flow of electrons. That is, current flows from negative to positive. Look at the electrical conductivity in metallic crystals. Alkali metals are soft and have low melting point. Alkali metals have only one valence electron. Alkali metals have only one valence electrons for each atom to enter the delocalization. Weak bond, so soft and have low melting point. It means that first A group elements are called alkali metals. They are lithium, sodium, potassium, rubidium, cesium and francium. Since francium is a radioactive element, lithium to cesium are collectively known as alkali metals. They belong to S block. And alkali metals have only one valence electron for each atom to enter the delocalization. Therefore, weak bond will be formed. So alkali metals are soft and have low melting point. Transition elements have a strong bond and have high melting point. Transition metals have strong bond and have high melting point due to the presence of more valence electrons. Other characteristics explained by free electron theory. Ductile and malleability. It is due to the non-directional nature of the metallic bond. Ductility and malleability is due to the non-directional nature of the metallic bond. This see the fact that on application of force, the metal ions can easily move from one lattice to another, leading to change in shape of the metal. Valence bond theory was proposed by Pauling. The structure of metals may be described in terms of covalent bonds that resonate among the alternate interatomic positions in metals. So, after free electron theory, which was proposed by Drude and Lorentz, let us discuss about valence bond theory. Valence bond theory or VB theory was proposed by Linus Pauling. According to this valence bond theory, the structure of metals may be described in terms of covalent bonds that resonate among the alternate interatomic positions in metals. A molecule or ion having such delocalized electrons is represented by several contributing structures, which are called resonating structures or canonical structures. All the properties of such molecules cannot be explained by one structure. Lithium metallic crystal. It reveals that one lithium atom is surrounded by 8 nearest neighbors in the metallic crystal. In lithium, its valence electron is present, which is insufficient to form 8 covalent bonds with 8 nearest neighbors. The resonance of electron pair bond takes place as shown. Metallic luster. When white light falls on clean and smooth surface, the valence electrons absorb energy and get excited into the nearest higher orbit. These electrons returned to the ground state and absorbed energy is released as visible light. This emitted light ray is responsible for the metallic luster. Now, electrical conductivity. Electrical conductivity is also one of the important characteristic property of metals. The bonded electrons in the metallic bond neither belong to a positive bond nor they are localized between any two atoms, so they are free to move and hence allow electrical conductivity. Next, higher density. The close packing of atoms in metallic crystal explain the high density of metals. If you observe the lattice structure of metals, close packing of atoms can be observed. This close packing of atoms in metallic crystal explains the high density of metals. Malleability and ductility. Due to the uniform charge distribution between the positive ions when stress is applied, the ions can change their position relative to their neighboring atom without changing the internal environment. After a discussion of valence bond theory, let us discuss the limitations of valence bond theory, which is also called resonance theory. The resonance theory explains the qualitative explanation, but it does not explain metallic character in the liquid state or in solution. Valence bond theory fails to explain the metallic character in the liquid state. For example, we take mercury. Mercury is a metal which exists in liquid state, but valence bond theory could not explain the metallic properties of liquid metal like mercury. Moreover, valence bond theory cannot explain the metallic character which exists in solution state. Now, molecular orbital theory. Molecular orbital theory. Two atomic orbitals of equal energy combine together to form two molecular orbitals. Two atomic orbitals of equal energy combine together to form two molecular orbitals by LCAO method. LCAO means linear combination of atomic orbitals method. Similarly, when three atomic orbitals are combined together by LCAO method, three molecular orbitals are formed. The energy of these molecular orbitals are very close and appear as continuous energy bands. Hence, this theory is also called band theory. Molecular orbital theory is also called band theory. If n number of lithium atoms are allowed to combine, they will form three energy bands. 1s band, it is formed by the combination of n number of 1s2 atomic orbitals. This band is completely filled, so it is the non-conduction band. 2s band, it is formed by the combination of number of 2s1 atomic orbitals. This bond is half filled, so it is the conduction band. The upper half of this band is empty, while lower half of this band is completely filled. 2p band, it is formed by the combination of n number of 2p subshells. This band is called empty band as it contains no electrons. Molecular orbital theory. The gap between 1s band and 2s band is called forbidden gap. As energy gap is very high here, so the electrons cannot be promoted from the lower 1s band to the higher 2s band. The level below which all bands are filled are called Fermi level. This may rises within a band or in the gap between two bands. This theory explains easily the properties of conductors and semiconductors. Molecular orbital theory easily explains the properties of conductors, insulators, and semiconductors. Now, insulators. As you know that the substances which do not allow to pass electric current through themselves are called insulators. Rubber, wood are the best examples of insulators. Completely filled valence band. More energy difference between the valence band and conduction band. Due to the more energy gap, the insulators cannot conduct electricity. Reason is given. Due to the more energy gap, the insulators cannot conduct electricity. Now, conductors. Less energy gap between The valence band and conduction band. Valence band and conduction band are overlapped. Electrons can easily move from valence band to conduction band. They can conduct electricity. Now, semiconductors. Less energy gap between the valence band and the conduction band. Promoted electrons in the conduction band and unpaired electrons in the valence band conduct electricity. Probability of promoting electrons rises with temperature. That rises with temperature. The conductivity of semiconductors increases with temperature. The conductivity of semiconductors increases with temperature. Hole is formed in valence band due to the transfer of electrons from valence band to conduction band. Look at the classification of types of semiconductors. Semiconductors are broadly classified into two. They are extrinsic conductors and intrinsic conductors. Extrinsic conductors are further classified into two types: p-type conductors and n-type conductors. Now, intrinsic semiconductors. An intrinsic semiconductor is one which is extremely pure form. Examples: pure germanium and silicon. Pure germanium and pure silicon, which have forbidden energy gaps of 0.72 electron volt and 1.1 electron volt respectively. The energy gap is so small. It is also defined as one in which the number of conduction electrons is equal to the number of holes. Extrinsic semiconductors. Those intrinsic semiconductors to which some suitable impurity or doping agent or doping has been added in extremely small amounts, about 1 part in 108, are called extrinsic or impurity semiconductors. Depending on the type of doping material used, extrinsic semiconductors can be subdivided into two classes. They are N-type semiconductors and P-type semiconductors. Now N-type. N-type semiconductors. N-type comes from the negative charge of the electron. In these semiconductors, electrons are the majority carriers and holes are the minor carriers. N-type semiconductors are created by doping, and intrinsic semiconductors with donor impurity. P-type semiconductors. P-type refers to the positive charge of the hole. P-type refers to positive charge of the hole. In P-type semiconductors, holes are the majority carriers and electrons are the minority carriers. P-type semiconductors are created by doping a intrinsic semiconductor with acceptor impurities. Thank you. अरे बसिरा, hello.